All right, we are beginning today with another different concentration unit. So going back to Tuesday, we were looking at the concentration units related to percentages. So mass concentration by mass, mass by volume, volume by volume, and they all kind of fit into the same general theme. I take whatever measurement of solute I have, and I divide it by whatever measurement of solution I have, and I multiply that ratio by 100 to get the percentage. Molarity works a little bit differently because with molarity, we are not concerned as much with the overall gross weight or volume of the solute, but rather in terms of how many particles of that solute are present there. And that's what gets us into this concept of moles. So when chemists refer to the concept of moles, what we're talking about there is a counting construct. So just like you would say that if I have 12 objects, you could call them a dozen objects. If I have a liter, it would be 1,000 milliliters. If I have a quart, it would contain 32 ounces. Those other unit labels all represent some amount of measurement or some amount of counting. Moles are in the same kind of idea. Only instead of counting ounces or instead of counting eggs or cookies, what we're counting instead are atoms, molecules, ionic crystals. And the number there is not nearly as rationalizable because the counting unit for a mole, 1 mole of anything is equal to 6.022 times 10 to the 23rd of those objects. That's a number that's a little bit more difficult to conceptualize. Because we start doing it in our head. Okay, 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion, 10 to the 15th is a quadrillion, 10 to the 18th is a quintillion. What am I on, 18? Yeah. Okay, so we're talking about, 602 heptillion objects. Can't even put our brains to it. We don't know what that is. I can't say, oh, well, it's the same as going to the bank and getting 100 pennies from $1. Or, maybe if I take a $100 bill and turn it into pennies. It's not the same thing. It's not even close. Now, why is it so big? Well, it's because atoms are so small. And so, if I take a spoonful of water, the number of molecules of water in that spoonful is greater than the number of spoonfuls in the ocean. It's just an unfathomable quantity that we are talking about. Now, where it becomes relevant for us is there is a link between moles and things that we can actually measure, masses. We finally get to that number at the bottom of the periodic table that we wanted to use so early on to describe the nucleus. I told you at the time, it's not about the nucleus, it's about mass. Well, now we get to use it because that number at the bottom of each element tells me the average mass of 1 mole of that element in grams. So if I look at carbon, Molar mass of carbon, according to the periodic table, is 12.01. So that means that 1 mole of carbon, that's 602 heptillion atoms of carbon, weigh 12.01 grams. I can run to a balance and measure out 12 grams. No big deal. That's the link. And so when we look at molarity, we're looking at a ratio of moles, giving us an idea of particles, a count, relative to the number of liters of solution that we have. And by definition, molarity being moles of solute per liters of solution, if I had a 1 molar solution of sodium chloride, that would mean that I had 1 mole of sodium chloride in every liter. Now, what does that mean in like concrete terms? Well, if I pull out that 1 mole of sodium is 22.99 grams, and 1 mole of chlorine is 35.45 grams. Well, if I add those two numbers together, 22.99 plus 35.45, I get 58.44 grams. So if I were to make this solution, I would know exactly how much I needed to do. I could go over to the balance, take out my table salt, measure out 58.44 grams of that salt, and then using something like a volumetric flask where it has a very defined value, this is exactly 1 liter. I can measure everything out, mix it together, and create exactly 1 liter with exactly 1 mole of sodium chloride. So there is some context here that we can kind of parse out. We just got to get to it. That's kind of the hardest part is thus far, we haven't talked at all about moles. How do we turn that kind of nebulous idea of, a literal crap ton of atoms into something that we can actually tangibly see and use? And that's where molar masses come in. So with that kind of information, now we can answer questions like these. What is the molarity of half a liter of sodium hydroxide if it contains 6 grams of sodium hydroxide? Well, the first thing I would want to do is I would want to figure out, well, what is 1 mole of sodium hydroxide in terms of its mass? And if I did that, I would say, okay, well, the sodium is 22.99. The oxygen is 16.00. The hydrogen is 1.01. And if I add those all together, that's where we get this 40 grams that they're talking about. So the first step would be to figure out how many moles there are. So I got to turn that 6 grams into moles. And so we got to go back to a skill that we, again, have largely abandoned the past couple of months, which is this unit conversion proportionality kind of skill. And to solve these, again, there's 2 ways to do it. This is the dimensional analysis unit factor conversion that we looked at, again, back in chapter 3. The other way that we looked at it was from a proportionality standpoint, if I have X moles over 6 grams and 1 mole is 40 grams, well, cross multiply and divide, I can solve for X. I'm going to get the same value. (40x) is equal to 6. X is equal to 6 over 40, which is 0.150. So this is a skill we already have. We've just kind of let it sit there dormant for the past couple of months. But now we can use it here where we have figured out the number of moles of sodium hydroxide. If I take that and divide it by the total number of liters, like so, that would give me my molarity, 0.300 molar sodium hydroxide. And so for molarity calculations, that capital M stands in as moles over liters. So if we're in the lab and we pick up a bottle and it says, 1 molar potassium chloride, it's going to say 1 M KCl. And the 1 would be the concentration, 1 mole per liter. M would tell you that it's molarity as opposed to percent. And KCl would tell you that it's potassium chloride as opposed to something else. All right, we're going to do several examples here, because this is one of those things that got to do it a number of times to kind of get used to the process. Once you do, you can kind of grind out every answer imaginable. But until you kind of have a good understanding of what you do first, what you do second, what you do third, this can be really difficult. So let's go through this again, piece by piece here. So I've got 34.8 grams of potassium nitrate in 0.225 liters of overall solution. First thing that I need to do is I need to figure out what is the molar mass of the potassium nitrate. So I've got potassium, I've got nitrogen, and I've got 3 oxygens. So for potassium, 39.10 grams. For nitrogen, 14.01 grams. For the oxygen, there are 3 oxygens. So it's going to be 3 times 16.00 for each oxygen. Put that all together, 39.1 plus 14.01 plus 3 times 16, we get 101.11 grams per mole. And now we have to go through the 2 calculation processes to get this concentration. I've got to convert this grams into moles, and then I got to divide that moles by 0.225 liters. So first step, again, we'll set it up as a proportion here, X moles are equal to 34.8 grams. 1 mole is equal to 101.11 grams. Cross multiply, I get 101.11 times X is equal to 34.8. So X is equal to 34.8 divided by 101.11. I get 0.344 moles. And that's moles of potassium nitrate. The last step, molarity is equal to moles of the solute over liters of solution. We now have our moles of solute, it's 0.344. And our liters of solution was given to us in the problem, 0.225. Our molarity to 3 digits would be 1.53 molar potassium nitrate, KNO3. So that would be B. Now, not every problem is going to follow this exact same construction. Some of them are going to go kind of in opposite directions. So maybe I know the molarity and I'm trying to figure out the mass that I need to weigh out. And again, we can work with that. We just need to kind of redirect our approach if we do. All right, any questions before we move? So MOL, MOLE, yeah, same thing. Capital M stands in for the moles divided by liters. So that's a specific combination unit. So if we were asked for a concentration, it'd be capital M. Because this is moles divided by liters. Nothing cancels out. So capital M stands in for that combination of units. Whereas here, it was just moles and grams. And I didn't put the units in here. But if I had, well, a little bit more than that, it would be, we would have had grams times X over here, and we have had grams times moles over here. So when we divided the 34.8 grams times moles over 101.11 grams, the grams would have canceled. We would have been left with just the moles. Okay, so that's I left that part out for brevity, but yeah, that's why we were able to say that the answer for X was moles and not just nothing. All right, other questions, things that we didn't quite get. Okay, so this is kind of the other direction that I was speaking about. We can use molarity as a conversion factor. Now, again, your book is focusing on the conversion factor from the standpoint of kind of a dimensional analysis kind of perspective. But understand also we could easily use this in a proportion if circumstances dictated that. So if we're told that something's 3.5 molar, that means that it's 3.5 moles for every 1 liter. Well, that's a fraction. I can put it in any order that I want to. I can put the 1 liter on top and the 3.5 moles on the bottom. I can flip it around and do the opposite depending upon what my circumstances are. Regardless, I can use this as a means to figure out how many moles I need to measure out or how many liters I need to measure out if I knew one but not the other. And the approach would be exactly the same, either a proportionality like what we have been doing, or unit conversion factor canceling like what your book has been showing. And the honest truth is, any of these calculation units that we work with either today or with Molarity would have the same kind of idea going about them. We talked about it on Tuesday as those percentages basically just turn into grams per 100 or milliliters per 100, depending upon your perspective. But the means would be exactly the same regardless of how we did it. So a question like this: how many grams of sodium hydroxide are necessary to prepare 75 grams of a 14% solution? Okay. On the surface, this seems like kind of an interesting, but not necessarily, I don't know exactly what to do right offhand kind of question. But again, if we think about what it means to be 14%, this becomes a lot easier to kind of look at. Because now I can look at this and say, okay, 14%, well, that means I've got 14.0 grams of sodium hydroxide in every 100 grams of solution. Well, the question's asking me how many grams of sodium hydroxide I need for a 75 gram solution. I can set this up proportionally. Cross multiply and solve. $100 grams of solution times X grams of sodium hydroxide is equal to 14.0 grams of sodium hydroxide times 75.0 grams of solution. Get X by itself, I need to divide each side by 100 grams of solution. On the left-hand side, the 100 grams cancel out. On the right-hand side, the grams of solution cancel out. The grams of sodium hydroxide remain. What's my value? Well, whatever 14 times 75 divided by 100 is. 14 times 75 divided by 100. I get 10.5 grams sodium hydroxide. That's letter A. So when we first visited this in chapter 3, this idea of calculating and doing these conversions, The thing I told you then is what I'm going to tell you again here. So long as our calculations are single step calculations, it's perfectly okay to set up a proportion, cross multiply, and solve. If that's in your wheelhouse, that's what you're good at, do it. Now, if we had multiple conversions to do, this would obviously get cumbersome pretty quickly. But luckily, we haven't asked you to do anything like that. And even more luckily, we're really not going to. All right, questions with this one? All right, you try this one then. How many liters of a 5.75 volume by volume percent ethanol solution can be prepared from 2.25 milliliters of ethanol? All right, so the biggest point of contention, the thing that we're losing sight of the most, is that this one's constructed slightly differently than the other ones have been. Each of the other examples that we did, we were given the total amount of solution and asked to figure out how much solute to put into. Here, we're given the amount of solute and asked how big does the solution have to be. So our X this time is in the denominator, not in the numerator. Now, because we're cross multiplying, it doesn't matter, other than if it's in the wrong position, it's going to give us the wrong answer. So if you got B instead of C, that's the reason why. The reason why is that fraction on the right, you flipped it, and it gave us the wrong interpretation. All right. Questions with this one? Again, that was the most common problem I saw walking around, was misinterpreting what the 2.25 milliliters was describing. It was describing the ethanol, not the solution. All right, we're going to try one more before we move on to something else that's not as calculation heavy, at least for the moment. So this is a molarity question. How many grams of aluminum chloride are needed to prepare 125 milliliters of a 0.150 molar solution? Now, right here, I will tell you, trick to this one, we are working backwards here. This is milliliters. Remember, molarity is in liters. So we need to take 125 milliliters and convert it to liters before we do anything else. All right, so this is an example of the scenario I was talking about before. Instead of taking a mass and converting it into molarity, we're going to use a molarity and a volume to figure out the mass. So we're working backwards here, but we can still use proportionalities to figure out what we need to do. So I'm going to let you think on it for a couple of minutes, and then we'll go through it together. All right, let's go through this. So again, when we go this direction, it's a little less straightforward. Because it was pretty easy to see when we were going the other direction. Okay, I do this, grams turns into moles, I plug it into the equation, moles divided by liters gives me my molarity. Here we're kind of working backwards off of that. So, some of the steps are still familiar. We still need to figure out the molar mass, but we're not going to use it right away. What we're going to do right away is we're going to try to figure out how many moles of aluminum chloride there are inside of this solution. So we set up this proportionality using the concentration, 0.15 moles in every liter is equal to X divided by 0.125 liters. Now, I saw some of you do this, and this is perfectly okay and smart as well. If you did want to convert milliliters into liters, you could have converted this liters into milliliters and put 1,000 milliliters in this denominator and kept 125 milliliters over here. Would have ended up exactly the same place. Nice thing about doing it this way, though, is when you cross multiply, you get 1 times X on the one side. So you don't need to do any further algebra. You just multiply the other two numbers together and you get what you're supposed to. So that ends up getting you 0.0188 moles of aluminum chloride. So that's the first part. We figured out the number of moles of aluminum chloride. Now, what we do with it after, again, this is the part that some of you really kind of had a hard time getting going on. And that was, okay, how do I bring together this molar mass idea with this unusual number of moles? Well, again, a proportion would work. Now, does this get a little cumbersome to do proportion after proportion? Yeah, it kind of does. In this case, set it up exactly the same way that we did the first one. Here's our known quantity, 133.33 grams for every mole. Set it up as equal to X over the number of moles that we just calculated. And once again, when we cross multiply, 1 times X means that we don't have to do any further algebra after we do the multiplication here. We get 2.50 grams of aluminum chloride, which is C. Now, if we were to do this another way, we could easily turn these fractions that we're talking about into dimensional analysis. So if the idea of doing, proportion after proportion kind of grates on you a little bit, which I completely understand, the way around that would be to do dimensional analysis. In dimensional analysis, what we would do is starting with our 125 milliliters of solution, we could use this fraction, and instead of setting up a proportion, we would set up the fraction in such a way that the denominator of the fraction matched the unit that we were trying to cancel out. So milliliters to moles here. There are 1,000 milliliters in a liter, and that gives us 0.150 moles. The milliliters end up canceling. And then to turn the moles into grams, again, we're going to use this fraction here. 1 mole of aluminum chloride weighs 133.33 grams. The moles would cancel. I'd be left with the grams of aluminum chloride. If I did this calculation, multiply by all of the tops, divide by all of the bottoms, 125 times 0.15 times 133.33 divided by 1,000 divided by 1, I get the same 2.50 grams. In multi-step kinds of problems, we can see where this is a beneficial kind of idea. The reason why we've hesitated to kind of feature it more prominently is, just kind of a feel for things. Generally speaking, I did this the first time, got a couple going, okay, I think so. What if I, switch that fraction, make it the wrong way? Don't know. I talked about proportions, everybody's like, I get proportions. So that's why I really hadn't mentioned too much of it since. So, but you can see, doing two sets of proportions, that, get a little bit bothersome. Any questions with this example? Matthew? Okay, so the answer to that question gets into a discussion of significant figures that we're not going to get into. So what we're going to do instead is we're going to use the cues from the problem itself. The problem itself had 3 measured digits: 125, 0.150. That's going to be what I use to figure out where to stop my rounding. So I'm not going to use any of these zeros because the zeros are meaningless. But once I get to that first non-zero value, I'm going to take 3 digits from there. Now, if I had 2 digits, I'd stop at 2. If I had 6 digits, I'd take it to 6. The fact that this is multiple choice kind of helps dictate that, because you can look at it and say, okay, well, they're rounding to 3 digits. I should round to 3 digits as well. But again, in your scenario, you're doing a calculation problem in mastering or something like that, and it's asking you, round this properly. That's the rule of thumb we should use. All right, other questions? Kenzie? So remember, molarity, the definition of molarity is moles of solute divided by liters of solution. So if I am told that I have a solution that is 0.150 molar, what that means is that there are 0.150 moles of the solute in every liter of the solution. And so that's, we can come up with these fractions like they're showing here. That's where this logic overall for why we can use this particular fraction exists. We're told that the solution was 0.150 molar. So we can break that into pieces based on that definition. 0.150 moles, 1 liter. Is that what you're getting at? Okay. All right, other questions, thoughts, concerns? Okay, we're going to get away from calculations, at least for a second here. There are some qualitative kinds of things, not number-oriented things, that are actually in your book in section 3, but we kind of skipped over them so that we can get into some of the number stuff. We're going to come back to them now. Solubility. In particular, gas solubility. So if I have an aqueous solution, what is the relationship between the solubility of a gas in that solution, and other factors. And for gases, it's actually really interesting. Because for the most part, we think of solubility as being a direct relationship to temperature. We increase the temperature, the solubility of stuff goes up. I heat up my tea, I can dissolve more sugar. I cool it down, it's not as soluble anymore. Gases is actually the opposite. There are two factors that go into gas solubility. The first of those factors is the pressure above the solution. Higher that pressure is, the more soluble that gas is going to be. Experientially, we've never thought about it this way, maybe. We already knew this. Take your favorite carbonated beverage, regardless of which one you're thinking of right now. It's under pressure. Why is it under pressure? Why is it stored with additional pressure inside of the can? So that the bubbles stay dissolved. As soon as you open up that top, pressure releases, and your beverage is now on the clock. The longer you let it sit, the flatter it's going to get. And the reason for that is when you opened up that can, you released the pressure. The pressure was holding those carbon dioxide bubbles in. And now that the pressure is lower, the carbon dioxide bubbles are starting to come out. Now we can prolong it if we screw the top back on if it's a plastic bottle. We can prolong that. We can prolong it by keeping the beverage cold. But eventually it's going to run out. Eventually it's going to become flat because the reality is carbon dioxide doesn't dissolve that well in water. But if we have a solution that is cold and under high pressure, we can get even things that aren't terribly soluble in water to dissolve in water enough for us to notice. The whole carbonated beverage industry. And the relationship there, that is something called Henry's law. So Henry's law relates those three factors: solubility, temperature, and pressure. And again, they're kind of opposite of what you think about. Usually you think high temperature, high solubility. For gases, it's the opposite. Lower temperature, higher solubility as a result. The other factor that we want to look into just briefly here is the concept of solubility of solids. Now, we've made a blanket statement on Tuesday that if we had an ionic compound and it dissolved in water, it was a strong electrolyte. And that is true. If we can get the ionic compound to dissolve in water, it'll result in a solution that is a strong electrolyte. But what if we have a compound that doesn't dissolve in water, even though it's ionic? Well, in those cases, obviously we're not going to get electrolytes because the stuff doesn't dissolve in the first place. And there are some guidelines that exist that help us to predict when solids are going to dissolve and when they are not going to dissolve. For ionic compounds are kind of complicated. Think about the process that goes into how a solution forms. The water has to rip those ions away from the crystal and hydrate them, surround them with water molecules. Well, in certain circumstances, the hydrogen bonding that forms isn't actually strong enough to break apart the ionic crystal in the first place. And what we get as a result are insoluble salts. And they follow these guidelines. Solubility rules. So some general solubility rules. If a compound contains one of these ions, it will dissolve in water. Absolutely, without exception.
By itself, or if there's anything,
Lithium with anything will dissolve. Potassium with anything will dissolve. Anything with acetate will dissolve. So when we say that it is soluble if it contains one of these, it doesn't have to be a combination of lithium and nitrates. It's any lithium compound dissolves. Any nitrate compound dissolves. Most chloride compounds dissolve. There are only 3 exceptions: silver, lead, mercury. Most sulfates dissolve. There's a handful of exceptions here. So your book gives you, and again, you're gonna have to go back to section 3 for this. Your book gives you a table, page 297, it's table 9-7. Gives you a listing of all of these rules. Again, just kind of general guidelines that we can follow that would help us predict when something dissolves and when something wouldn't dissolve. And for the most part, it follows along some really simple to follow guidelines. You don't have to memorize all the guidelines. This is, again, it's an example of something I would give you on an exam. But the utility of these is actually really kind of cool because thanks to some of that insolubility stuff, barium sulfate is a white solid, bright white solid. Well, you have a bright white solid inside your intestines, guess what? It's going to show up on an X-ray really, really well. And that's what it does. So we use this chemistry sometimes to help us with other kinds of applications. So helping to make clear imaging for kind of GI tract kinds of things. That's one example. And what it'll allow us to do is it'll allow us to answer questions like these. If I'm looking at each of these, we can notice that there are solids forming in each one of these test tubes. Why are they forming? Well, this is where we can get into those solubility rules. So if I look at, this is kind of an incomplete list. But if I look at this list here, it's insoluble if it contains the sulfide ion. Well, cadmium sulfide and iron sulfide will contain sulfides. So why are these precipitating? Why are these insoluble? Because of the presence of sulfides. Why is the lead 2 iodide forming here? Well, go back to our iodide. Iodides are usually soluble, but the combination of lead with iodide makes it insoluble. Nickel 2 hydroxide here. I look, hey, hydroxides, usually insoluble. So thanks to solubility rules, I kind of have an idea of when things are going to be soluble and when they're not going to be soluble. And I can start to piece together why some things behave the way that they do. All right, last thing that we're going to get to today, and we're only going to get to touch on it, is one more calculation piece here, and it involves dilution. So we all know what dilution is. Take something, you add water to it, it becomes less concentrated than what it was. The example they're giving here is frozen concentrated orange juice. Buy that stuff in the store, it's a brick. Doesn't taste pretty good on its own. It's still sold in the store.
But that doesn't mean.
I know. Yeah, so, yeah, for context, if you were poor. If you were poor and you couldn't afford regular orange juice, going back to the 80s and 90s, you would buy this stuff. It's basically just orange pulp and boiled down juice, frozen together into a mollusk. And you add water to it, and you get some sour orange juice as a result. So dilution processes involve a couple of things. We're adding water. And as a result, we're seeing an increase in the volume of the overall solution without changing anything about the solute itself. So the amount of solute stays exactly the same. We've increased the amount of solvent, and we've increased the overall volume of the solution. So as a result of the volume increase without the change in solute, we see a dropping in the concentration. The question is, how do we quantify this? And the answer is with a relatively simple equation. Now, your book is presenting these as two different things. In reality, it's the same equation. We're taking the concentration of whatever it is and multiplying it by the volume of that particular solution. And we're setting that equal to the diluted concentration and the diluted volume. So it doesn't matter what equation we use, so long as two things are true. The concentration unit that we use has to be the same on both sides of the equation. So if I'm using molarity on one side, it's got to be molarity on the other. If I'm using mass percent, it's got to be mass percent. If I'm using volume, it's got to be volume. The concentration units on both sides have to equal out. And the other thing is that the volumes have to be of the same unit. So if I'm measuring 1 in milliliters, I got to measure the other 1 in milliliters as well. If I measure it in liters, it's got to be liters on the other side. So long as those two things are true, these equations are exactly the same. And the beauty of it, I don't need to convert any of the units into anything else. So if I'm given milliliters, I don't need to convert it into liters first. And that's a really important thing because multiplying and dividing by 1,000, not that it's hard, but it's easy to make a mistake. You hit that 0 button twice instead of 3 times. You get the wrong number, start to wonder why mastering is counting you wrong, why mastering hates you so much. So this is kind of a walkthrough of one of those kinds of problems. Unlike the ones that we were talking about at the beginning of today, there are really only 2 types of problems here. One where we're looking at concentration changing, one where we're looking at volume changing. The equation usage is exactly the same in both. So if I'm asked to figure out what the final concentration is, what I need to remember is just I need to remember to cluster together the things that are describing the same solution. So this 1/2 liter of 6 molar, this is our first solution. The final volume of 1 liter with our unknown concentration, that's our second solution. And so from that standpoint, if I'm doing C1 times V1 is equal to C2 times V2, I can put that all together, 6.0 molar times 1/2 liter is equal to the unknown concentration times 1 liter. No cross multiplying this time, it's just simple algebra. I'm going to divide each side by 1 liter. Liters cancel on this side, everything else cancels over here. 6 times a half divided by 1 is 3. Didn't even need my calculator for that. But even at that, no, you won't be able to do them in your head necessarily, but the process would be exactly the same. So yes, I understand the first example that we get out of the textbook always looks so easy because they give us the simplest numbers to work with and you can do half of the calculations in your head. But understand that the process here is what's important and the process doesn't change. So this is where I will pick up with the bonus video for placing on Monday. So I will pick this up and I will finish out the chapter. And we'll take it from there. Have a good weekend. See you Tuesday for the test. Don't forget about the study session tomorrow at 10, if you can come. Yes. All right. Well, then watch it on YouTube this weekend.